um, energy problems with torque and with momentum, but things you don't, things that won't be, what are you doing, dog? That won't be on final. And I know I spelled things wrong, sorry. What is it? Equilibrium, meaning the problems where you have like a ladder or a beam, we won't do anything like that. We probably won't have collisions. If we have a collision, it'll be something where you use conservation of momentum, but as far as like doing the one-dimensional inelastic, elastic collisions, that won't be on there. So you can skip that stuff in general. And then really, if you look back at the practice exams for exam 2, they're probably better than even studying exam 2 as looking for stuff. But I'll go over that later. I just, if people want to end up getting out of here, that I wanted to make sure that you knew, don't worry about equilibrium, don't worry about collisions. Mostly concentrate on these 4, and then make sure you know how to do like a problem with pulleys and ropes, and maybe an incline. So as far as error, so one of the things I noticed in Impulse was a lot of people had problems determining delta M. You guys got the equation right, but everything else was, that part seemed to give some people some trouble. And I want to talk about this. So the equation for impulse is force times time is equal to the change in momentum.
Professor Boyd?
Yes, ma'am.
This is Alexis. Before you keep going, is it okay if our class shows you something real quick?
Oh, absolutely.
If you could stop sharing your screen, that would be great, just for a minute.
Yeah,
but
absolutely. Sorry.
Yeah, so we just wanted to say thank you so much for being such an amazing and understanding professor. During this time, it's been really difficult to adjust to the virtual learning environment, not just for us as students, but we understand it has been uniquely challenging for professors as well. And you've been so patient and empathetic during this time, and we just wanted to say huge thank you.
Well, thank all of you. It's always a pleasure to teach you guys. And I don't know what to say. That's really sweet. No one's ever done that for me. So thank you all.
Thank you for everything, Professor.
Yeah,
thank you so much.
Thank you so much, Professor.
Thank you.
Thank you, Professor. You're seriously my favorite professor that I've ever had. You've been so understanding, and we just appreciate you so much.
Well, thank you. I'm actually amazed at how many students that I get that are active in government, that have gone on to NASA, that have gone on to doing just amazing things. And I really do try to support you as much as I can. So that means if you guys need letters, don't hesitate to ask me. If you need help with something, don't hesitate to ask me. One thing that I really, it's really important to me is that you all do well in 4B and 4C, that you leave the class feeling better than when you got here. And I know a lot of you have. A lot of you have spent a lot of time texting me and talking to me, and that's really good. And I urge you to do that with all of your professors. Make the most of it. College is short, and you guys got robbed so bad of not being on campus and not being able to spend time together and go grab a coffee and just sit and enjoy each other. So I feel horrible for that for you guys, and I just want you guys to do the best you can and be the best. I know that sounds like every professor, but I do mean it. And I know that a lot of you have had a chance to talk to me. But honestly, if you need help, if anything's happening, if you just want to bounce an idea off me, you have my email, you have my text. Feel free to text me, even a year from now, and just say, hey, Professor Boyd, I'm not sure what to do here, or I really struggled in 4B and I'm worried about 4C, and I'll talk you through it. So, but thank you, Alexis, you're great. And I hope everything's going well for all of you. I hope we're in a danger zone right now, you guys. Please be safe over Christmas. The numbers are going up again, and that's the worst thing in the world. And just be safe. Do what you can. I know it's horrible. I'm going stir crazy too. I miss museums. I miss going to the Long Beach Aquarium. I miss all those things, and it'll hopefully 3 months from now. So hopefully by summer we'll be good. But I wish all of you a happy holidays, and I hope my final is a good thing and not a horrible thing. I hope you guys aren't panicked, and I know some of you are. So let's jump back into this. I'm going to share. Thank you so much, Alexis, by the way.
Thank you. We wish you happy holidays too.
Happy holidays, Professor.
Thanks, guys. So again, like I said, this is something that I've noticed some people having problems with. If we had this equation and we solve it for mass, so we have V final, V initial is F of T, and then so the mass is F times time, force times time, V final minus V initial. When you do error, anytime you have an equation, and I'm going to try to do this, so we're going to try and find it for delta M. Essentially what you have is the error associated with each variable squared, and then take the square root of the sum of them. So we're going to have the error associated with F, and with T, and with V final, and with V initial. And so here's how we find those errors. If we have a function, what you do is you take the partial of the function with respect to whichever variable. And I know I didn't draw that correctly. Sorry, guys. I've always been accused that my partials look like 2's. But all this symbol means is that you take the derivative with respect to whatever your variable is. So looking back here, we have M is ft over v final minus v initial. So we would take the derivative of the function m with respect to f. That would mean that we hold all the rest of it as constants. And what we get is we get t v final minus v initial. The next thing we do is we multiply by the measurement error of x. So when we did our force, we had a measurement error. And to go one last step here, this delta always means your measurement error. It's the error associated with if you have a ruler or you have a readout, like a digital readout of 1.0156 or something. On a ruler, the resolution is half, or I mean the resolution is the smallest mark, and half of that is your delta. So delta x is half of the smallest mark. Here, the resolution is the smallest digit, the lowest digit, and half of that digit, half of that smallest digit is your error. So delta x is half of the smallest. So here, if these were little millimeters, right, and these were 0.0001, what you get is you get delta x would be half of 1 millimeter, or it would be 0.0001 to the half. Or so this would be 0.0005 meters or 0.00005. So half of the smallest digit. Whatever on ours for the force, I don't remember what it was, but I think it was 0.0005. I think we had 4 digits. Let's pretend we did. So we multiply this by delta f, because that's what we're taking this by. And then the final thing that you do is you divide it by the actual function. here. So we would divide this whole thing by m again, by f t v final minus v initial. And you can see what happens here is t cancels, v final minus v initial cancels, and what we're left with is delta f over f. So the measurement of the force divided by the actual value that we got for the force in there. So that is how you do it when you have the error is the function, the partial derivative of whatever your function is times the uncertainty, measured uncertainty, divided by the value of the function. And you just put those in here and here and here. If you have the other way we did it, where we did delta f over f was standard deviation over the number of data points and then divided by f, you can see that delta f is the standard deviation over the number of data points. That's what you do when you have a I'm losing my train of thought here. When you have a large collection of data points and you want the standard deviation over n. So either you either use this or you use standard deviation, square root of the number of data points divided by the function. Those are the two things that you use to get the error associated with each individual variable. So make sure, go back in, and every single lab handout I have, it shows you this, it looks like this. It'll say like delta f over x times delta x, I'm sorry, partial of f over x, delta x over f squared, and it'll say like delta f or partial of f with respect to y, delta y over f squared for some function error. And then I give you the actual breakdown of that given whatever the function is. So make sure if you guys don't know how to do error at some point before you get to 4B or 4C, go back and reference that and see if you can make sure that you know how to do that correctly. The reason why I didn't take points off is we just don't have enough time. And I feel like your labs, you should always be able to correct them for certain things. And I didn't want to tank a bunch of your lab scores. And really that was the only thing that I saw that was like, honestly, kind of wrong. There were little errors. Those of you that turned it in, whoever in your group turned it in, I gave you my notes and said, hey, this was wrong, this was wrong. But in general, they were really good. The other thing that you need to make sure you do for 4B and 4C, a lot of you still want to do the conclusion in, like, you answer each part in short sentences. Do it as an essay. So like the first paragraph should talk about your findings and the error associated with them. The second one should talk about your further findings and how good your data is, like your R-squared values for your graphs. Then you need to talk about where your error possibly came from and causes of it. And the last thing that you talk about is how you would make the actual experiment work. So we've gone through that every time. And I know you haven't gotten the feedback that you really should. I need to do a better job of that. I definitely can, but I mean, we're doing this remotely. And unfortunately, we just don't have the one-on-one time that I can go through in lab and show you what's happening and help you correct your data if you're getting bad data. But hopefully that makes sense and you'll be okay in 4B and 4C. I just honestly don't want you to get to 4B or 4C and not know how to do error. And then they're like, who was your teacher for 4A? And you're like, Professor Boyd, which is okay. What happened here? Anyway, so on to chapter 15. And chapter 15, I normally divide up into pendulums and oscillations. Unfortunately, we missed a day because of fire. And so I ended up doing it all at the same time. But for pendulums, the equations are quite simple. really you just have a period equation. And that period equation is 2 pi times I over mg r, where r is the radius of gravitation, of gyration. But remember that for a simple pendulum, I is a point mass, and a point mass has a moment of inertia of ml squared, and the radius of gyration, rg, is L. So what that really means is, imagine you have a pendulum, you have a little simple point mass attached to it, it's going to swing back and forth. It has a length L. So the moment of inertia for a point mass rotating about an axis of rotation here is m times the distance away from the axis squared. So that's ml squared. The radius of gyration is the distance from the axis to the center of mass, and obviously a point mass, the center of mass is at L as well. So what this turns into is 2 pi ml squared over mgl. The m's cancel and 1 L cancels, and you get L over g. But I want you to remember this, because sometimes you have, for let's say a rod, instead of a point mass, a rod about 1m, I would be m L squared over 3, and the radius of gyration would be to the center of mass, which is at L to the half. And when that happens, what you get is you get that T is 2 pi 2/3 L over G by plugging these into here. So the only hard thing on a pendulum really is if it's some weird shape that you have to change the center of mass, and or you have to change the moment of inertia, and you have to account for the center of mass being at the center. At most, on the final, you're going to have maybe a rod, and maybe not even that. I'm not going to make you do some complicated moment of inertia for the pendulums. And so you can see you really have one equation there. And that one equation, as you'll see when we do the problems, means that the problems are pretty simple with pendulums. They're not too bad. I'm going to skip this one for a minute and get to a pendulum one, and we'll come back to these. That's a pendulum, but we'll come back to that. I don't know what happened here. So this is, well, never mind. I'll just start it at number 1. The second thing that we have is we have the thing that you just did, which is oscillations. And in oscillations, our goal is to get this equation x sub t, x max cos omega t plus phi. And you need to be able to figure out what the amplitude is, what omega is, and what phi is. So we find these, and once we have those, the velocity is the derivative of x with respect to t, so it's just negative omega x max sine of omega t plus phi, and a is the derivative of that with respect to time, the derivative of velocity, or the second derivative. If you're wondering where the negative sign comes from, the derivative cosine with respect to t is negative sine with an omega out front. So once you have this equation, you can get v, you can get t. And so our job is usually to find the amplitude, x max, omega, and phi. Omega, I think my stupid Wacom tablet is acting weird. Omega is k over m, and the other thing to remember is that if it's a pendulum, omega has only to do with the frequency of the period. It has nothing to do with the actual motion. It does, but it doesn't. You will see that in one of these problems. And then frequency is equal to 1 over period. Period is equal to 2 pi over omega. So if you have the period, you can get omega. If you have k and m, you can get omega. vice versa. So our first problem is an electric shaver. An electric shaver has a little blade that moves back and forth, and they tell us right away that it moves back and forth over a total distance 0.0019 meters. And it has a frequency of 117 hertz. So it asks us for the amplitude and the maximum speed and the maximum acceleration. So we always start these. We want to find x of t is x max. We don't particularly need to here, but I wanted to make sure. So the amplitude is half of the total distance that it can travel. So this, there you go again. So for A here, it's just d to the half, and you can see that it's 0.95 millimeters. I have it in meters, but half of 1.9 is 0.95. So we have x max. Then, since v of t is negative omega x max sine omega t plus v, and they want to know the maximum. The maximum occurs when this is 1, and if that's 1, then it's just this value, take the absolute value. And so all we have to do is multiply omega times x max. Well, what is omega? If we have the frequency, 2 pi times the frequency is equal to omega, or omega is equal, or the frequency is equal to omega divided by 2 pi. The period is 2 pi over omega, and the period is the inverse of the frequency. Frequency is the number of times per second. Period is the number of seconds per time. Like how many seconds does one oscillation take? Frequency is how many oscillations in 1 second. So all we have to do here, though, is multiply 2 pi times f by our amplitude, and we get the maximum of the velocity. The maximum of the acceleration is similarly negative omega squared cos of omega t plus phi, and that happens when cos is 1, so it's really just this part, which means we just multiply 2 pi f, square it, multiply it by 9.5. Oh my God, what is going on? Okay, and that's it. So what we have from here is so what we have is 2 pi f is omega, and if you have some total oscillation distance d, then x max is half of that. And finally, that v max is omega x max, and a max is omega squared x max. That's what you were supposed to learn from this problem. Moving on. Another simple harmonic oscillator is a block with a mass. So we're given m and a spring constant of 490 newtons per minute. When the time is 0.7, they give us the position and velocity values. And these are both positive. Oh man, I hope that gardener is not coming right now. So in this, it asks what is the amplitude, what is the position in the block at time t equals 0. I think my gardener's here, and hopefully he won't be absolutely annoying. So again, what we need is x of t is x max. I might have to turn this off for a second. Hold on 1 second, I'll be right back. Okay, I'm so sorry. I'm gonna go through this, and if I end up muting it, it's because the gardener's working out back. I'll try to go through what I did, but I'll do the math while it's loud here and try to explain it. So we need to find the function x max cos omega t plus phi. And this problem is a lot like one of the ones in your book. Since v of t is negative omega x max sine of omega t plus phi, and a of t is negative omega squared x max cos omega t plus phi again. And we know that omega is k over m. We have omega. We don't necessarily have the amplitude. That's the first thing they asked us for. But we can find it. It's just going to be a little bit hard because we don't know phi. So first things first, if I take v and divide by x, what I get is I get negative omega x max sine omega t plus phi over x max cos omega t plus phi. And remember that we were told that at t is equal to 0.7, we were told that x was 0.18, x at 0.7 was 0.181, was it? And v was 3.570. So when I do this, if I take v over t, x over t, when t is 0.7, I get the x maxes cancel. I get negative omega over sine over cosine, which is tangent of omega t plus phi. Therefore, I know that t is 0.7. I know that v of t and x of t are 3.570 and 0.181. If I divide by negative omega, that goes away. Omega here was, I'm just going to do the math as I go, and hopefully you can follow it, and then I'll So So on this one, the problem is that I'm getting a positive number, and you can see the answer was actually negative. The reason for that is that when I got this answer, tangent of -1, I got negative 0.108. But I can always add pi to that because it's tangent. It could be the answer, or it can be the answer plus pi. So if I add pi to this, which is what I need to do, I'll actually get a negative answer here. This will actually become -1. So to show you that, I got 0.181 plus pi, this was negative, minus 127.05. And what you'll end up seeing is that I get 0.181 plus pi, pi minus 0.181 minus 127.05 gives me negative 124.0894 rad. And when I plug that in for my phi here, instead of why did that give me, okay. So when I plug in, instead of this, I plug in 124.0894, 181.5 times 0.7, which is omega times t, minus 124.0894 4, I get 2.9. Cosine of this answer is -1-ish. There's some rounding in there. And so this becomes -1 and this becomes a negative. Wiley does some weird stuff with rounding, which is why this isn't exactly lining up. But the main takeaway on that is that whenever you have tangent of some function, it's going to give you two angles. The angle that your calculator gives, and you have to always assume there's another angle. The only way to know whether or not it should be one angle versus the other is to look at the velocity at that time. And that's more work than I want you to do on these. As long as you give me the correct tangent angle on an oscillation, it'll be fine. But how you find it in this case is you do V at some t, in our case 0.7, is equal to -omega tan of omega t plus phi. Knowing that t is 0.7 and knowing that omega is 181.5 rad per second, we can solve this equation. And knowing VAT and x of t, we can solve this equation for phi. Once we have it, x of t, and again, we can use that value, 0.181 or whatever, x max cos omega t plus phi. Now that we know phi, we know omega, we know t, t is 0.7, phi is whatever it is, we can plug those in and we can find x max. It's not too bad. There's a problem like it in the chapter. And then the last thing is, so what is the position and velocity when time is 0? Well, when time is 0, you can see that x max here, if t is 0, all you get is the phi part. So x at time 0 is x max cos of omega times t, and v at 0 is -omega x max sine of omega t. I'm sorry. And I apologize again for my gardener being here. I don't have any control over when he comes. That you can see, you can just plug in numbers once you know them, once you know phi. The only weird thing in this problem for Wiley is that you sometimes can get a weird number for phi, and you might have to add pi rads to it. Okay, this problem's actually not so much a oscillation or a pendulum problem. It's actually more of a uniform circular motion problem. So they've given us a function, and in this function, I can see that instead of x, they're using theta. But it's exactly like x of t is equal to x max cos omega t plus phi. This was what the worksheet was about. They basically turned a pendulum into an oscillatory function with this x describing the motion. So we know that omega is 6.4 here. And they want to know the pendulum's length. Well, the period is 2 pi omega, or omega is L over G for a simple pendulum. That's what we found, that T was 2 pi times L over G. I'm sorry, I had that flipped down here. And because this is 2 pi over omega, omega is the inverse of L over G. So knowing that, we can get that L is G over omega squared. Square both sides, multiply through by L, divide through by omega squared. So once we know that, this is actually really easy to find. The maximum kinetic energy, on the other hand, isn't as easy. So you might not remember back when we did energy, and I hope you do, but that because it swings back and forth, it passes through this low point. It passes through a point where H, and where H is 0, and where H is, I'm going to call it big H. The energy at the top, it has no velocity. So the energy up here is just mg big H. When it goes through the bottom, it only has mv squared over 2. So the energy at any time would be mgh plus mv squared over 2, but the energy at the top is equal to the energy at the bottom, and at the bottom, h at the bottom is 0, h at the top is big H, v at the top is 0, and v at the bottom is v max, right? So it goes between the two. So what we really have is we have mgh is equal to mv squared over 2. It wants the maximum kinetic energy. This is the maximum kinetic energy. But now we have a small problem. How do we find h when all we know is L? If I have a pendulum of length L and it comes up to some height h, this distance here, because this is L and this is some angle, this distance here is L cos theta. So h is L minus L cos theta. So mv squared over 2 is equal to mg L times 1 minus cos theta. And they gave us, they didn't give us the maximum, but they gave us this equation, and x max occurs when cos is 1. So we know that theta max is 0.098. And if I put that in for this angle, so what I get is that mv squared, which is the kinetic energy, is equal to mgl 1 minus cos theta max. And theta max is simply 0.098. So it's not too bad. We found L was g over omega squared, and we got omega, and we got theta max from the function. So just make sure you understand that. It's kind of a tough problem, and it's not a tough problem at the same time. I understand it's tricky. It's about as tricky as you can get with a pendulum and energy and oscillations all rolled into one, which is kind of cool. Okay, so we have a thin rod. This is actually a pendulum problem. And on the final, I label everything. So it'll say like pendulums, and you'll know which one you're talking about. But here we have a thin uniform rod about some axis, and it's going to go back and forth. They tell us the mass, and they tell us that the period is 1 second. And that it has an angular amplitude, so the biggest angle that it makes is going to be 2 degrees, whatever 2 degrees happens to be. And we want to know the length of the rod. When we're dealing with pendulums, this is why I said don't memorize L over G, memorize I over mg R. R here, the center of mass is at L to the half. So R is L to the half in the bottom, the radius of gyration. I, for a thin rod about one end, is ml squared over 3. Therefore, the period is 2 pi 2/3 L over G. We know that t is 1 second. We can solve this by squaring everything. So we get 2t squared, 4 pi squared, 2/3 L over G. Solve that for G, and you get that L is t squared times 3G divided by 8 pi squared. T is 1 second, G is 9.8. Once we have that, what is the maximum kinetic energy of the rod as it swings? And now here things get a little weird, because exactly what we did before, mv squared is equal to mg L 1 minus cos theta, although it's not L now. Now we have to take it from the center of mass, L to the half, L to the half. And so this is actually L to the half cos theta, and the height from here to here is L to the half minus L to the half cos theta. That just means we just have to turn that into a half, and we're good. Okay, so if you're having trouble with this one for some reason, it was maybe because of the half. So that problem's not too bad because it's a lot like the previous problem. You just have to remember the physical pendulum instead of the simple pendulum. This problem is really about energy and understanding energy. The energy at any time in simple harmonic motion is kx squared over 2 plus mv squared over 2. But if we plug in for x and v, x is x max cos omega t plus v, and we plug in for v negative omega x max sine omega t plus v. What we see is that this becomes k x max squared cos squared, and that's all I'm going to put. This becomes m times omega squared x max squared sine squared over 2. But omega squared, because omega is k over m, is square root of k over m, is k over m. So this becomes k. And what you see here is cos squared plus sine squared is 1. So really the energy at any time is kx max squared. But this and this is the spring potential. This is the kinetic energy. This is mv squared. That being said, they ask us, well, what fraction is the kinetic energy when x is equal to 1/6 x max? So what we have to do here is we have to divide the kinetic energy, if my stupid pen will decide it wants to work. We have to divide the kinetic energy by the total energy. So what we have is we have k x max squared over k x max squared over 2 and times sine squared of omega t plus phi. And here's the tricky part. When x is equal to x max to the 6th, x max cos omega t plus phi, this right here has to equal 1/6. I think you guys understand that, right? This has to equal 1/6. So the potential energy is equal to it asks first for the kinetic, then the potential. But I'm sorry, the potential energy of the spring, which is k x max squared over 2 cos omega t plus phi squared, and that over the total energy, k x max squared over 2, means that what we get really is cos squared omega t plus phi, but we already know that this has to equal 1/6, so we get 1/6 squared, which is 1/36. I answered part B first, but if the potential energy is 1/36 of the energy, then the kinetic energy is 35/36 of the energy. It's just easier. I didn't want to tell you to like find omega t plus phi and then put it into sine and figure out what that is. You can do the potential energy part first and then find what the kinetic energy is, or do the kinetic energy first and find what the potential energy is. And then finally, it says at what displacement, so what value of x is the energy of the system, half the kinetic and half potential. So we want to know what is x t when k x max squared to the half times a half is equal to kx squared max to the half times cos omega t plus phi squared. Now what this is saying is half the total energy, and this is equal to the kinetic energy or the potential energy. So this is half the total energy is equal to the potential energy. Now seeing that, we can see that these cancel, and what we get is that 1/2 is equal to cos squared omega t plus phi. Obviously, if I take the square root of both sides, well, I'll just leave it like that. I get that cos of omega t plus phi is equal to root 1/2. And so that means that x is equal to x max cos omega t plus phi, or x is equal to x max divided by root 2. And if you didn't follow that, just go through it nice and slow. Half the energy has to equal the potential energy. So 1/2 of k x max squared over 2 has to equal k x max squared over 2 cos squared omega t plus phi. Cancel this stuff off, and you get that 1/2 has to equal cos squared of omega t plus phi. And if I take the square root of both sides, that means that cos omega t plus phi is root 1/2. Plug that in, and I get that. You could do the same analysis for the kinetic energy if you wanted to. And you can see that if this is our, at what displacement in terms of amplitude, this is 1 over root 2 of the amplitude. Weird question, but yeah. All right, we only have 2 more of these, and then we'll get on to final stuff. Stop, please. So an oscillating spring block system, I actually love this question. An oscillating spring block has a mechanical energy. So the energy is 4.12 joules. That is kinetic energy plus potential energy. That's the total energy. They give us that it has an X max, an amplitude of 0.0618 meters. It has a maximum speed. So V max is 4.29 meters per second. And they want the spring constant, the mass, and the frequency. So, okay, knowing these things, first of all, what do we know? We know that V max occurs when negative omega x max, sine of omega t plus phi is 1, and I can get rid of the negative sign. So omega is simply V max divided by x max, and they gave us both of those. We also know, so we can find omega. We know that omega is equal to root k over m. We don't have the mass. Do I need to do that? Maybe I didn't need to do that. So we want to find k. I know that the energy, oh, I know what I did wrong. So the energy total is k x max squared over 2, and I know x max. So k is 2 times this energy over x max squared. It's 2 times 4.12 divided by 0.0618, and you'll get that number. The mass of the block, now that we know k, we can find that m is equal to k over omega squared. Square both sides, move the m over, move the omega over, and we're good there. And then the frequency is equal to omega divided by 2 pi. Or it's 1 over the period, but the period is equal to 2 pi over omega. So either way, you want to see it. It's a really fast question, but you have to know what equations are important and you have to know what it's telling you. So that's not too bad. I like questions like that because they're really fast if you know what you're doing. And if you don't, then you're just going to make a mess of it. All right. Last one we're going to do is a damping. We will not have damping on our final, but I wanted you to see it. In damping, there's a new omega in the function, and that omega is the square root of k over m minus, double check and make sure that I give you the right equation because I just don't want to tell you lies. Yeah, b squared over 2m. And then, that's an m. The actual x equation for damping when you have friction is x max times exponential minus b over bt over 2m times cosine of this omega prime t plus some phase angle. And so here they ask us, after giving us a bunch of information, the time for it to reach a quarter of its value and then how many oscillations. This is really important though. Even without damping, understanding that part is kind of important. So the first thing we would need to do here is find omega prime. And we can find omega prime, well, we don't have to do this. Actually, never mind, I don't need to do that. I take that back. They gave us that the mass was 2.1 kilograms. They gave us that K was 14 newtons per meter, and they gave us that B was 250 grams per second. And they told us that it is pulled down, so X when T is equal to 0 is 0.102. All right. And they want to know how long until it takes to get to fourth. The amplitude for damping is the X max times e to the minus bt over 2m part of this equation. This is actually the periodic part. Remember that when it's damped or has friction, what happens is it's still periodic, but it spirals down. And this part is the X max e to the minus bt over 2m. This part is the cos or sine part of it, the cos omega t plus phi. So basically you have a decreasing amplitude with time while the period stays the same in general. So what that means is that we want to know t when x is 1/4 of the initial x max. So that means 1/4 is equal to x max e to the minus bt over 2m. And here's where you may have some trouble. So 1/4 equal to exponential minus bt over 2m. First of all, I can take the ln of both sides. That brings this down. Ln of a over b is ln of a minus ln of b, and ln of 1 is 0. You can't have negative ln's. So what I have here is I have ln of 1 minus ln of 4 is equal to negative bt over 2m. This goes away because it's 0. And t is equal to negative 2m over b times ln of 4, which is 2m over b. 2m over b times ln of 4. We had m here and we have b. Make sure that b is in kilograms, I think. Yeah. make sure that B and M have the same units. So if you want to put this back to, this is 2,100 grams, or this is 0.250 kilograms per second. But they need to be in the same units. Once you get this time, there's a important thing here. So if you have some time interval and you have a period interval, so let's say you have a time of 10 seconds, right? And your period is 1 second. To find out how many periods have happened in that time, you take the total time and divide it by the period. So I would get 10 divided by 1, and that gives me 10 seconds. So this is seconds per period. This is 10 seconds. If I divide that, I get 10 periods, right? So what we need is we need to know whatever this t ends up being, divide it by the time of 1 period. But the time of 1 period in this case will be 2 pi over omega prime. So you do need to put in your k, your m, your b squared, your 2m, and figure out what this number is. And that way you can get the period and then take the little t and divide it by the period, and you'll get the number of periods that have happened in that time span where the amplitude was reduced to a fourth. I'm not going to do all that, but that's what you do for this problem if you're having problems. All right, so on to fun stuff. These are the problems from the practice final. The first two are pendulum problems, the second two are oscillation problems. These are probably more useful because these are problems I wrote. So in this problem, we have an asteroid with a radius of 3 × 10⁵ meters, and it's spherical, which tells you you know it's a sphere. We're going to need the volume in a bit. And that's what that's telling you, is it's telling you it's a sphere. The astronaut standing on the surface creates a pendulum using a 1.5 meter string. That's important as well. So this is important. The fact that it's spherical is important. And once in motion, it has a frequency of 0.165 hertz. Now, what is the period of this pendulum? We know the period is 2 pi over omega, or it's 2 pi L over G because it's a simple pendulum. We don't know what G is, though. We do know this, so we can use this part. We don't know G. We know G on the surface of the Earth, but that's not what this G is. This G is something new. So we have that omega is 2 pi F, and we have the period is 2 pi over 2 pi F, which is 1 over F, which is 1 over 0.165. I believe it's like 6 seconds. Once we know that, though, we can use the period is 2 pi L over G to get G. Square everything, solve for G, and you get G is equal to 4 pi squared L over T squared. So whatever your T is here, your L is 1.5, and you get that answer. And the solution's online. It's on our Canvas. Now, what is the mass of the asteroid? We know that Newton's law of gravity, assuming that the only force on him is the force of gravity, is Gm m over r squared. This is his mass, and our A is this same G. So what we get is that G is equal to Gm of the asteroid over r squared, or the mass of the asteroid is equal to G r squared over big G. Big G is 6.67 times 10 to the minus 11. R is the radius of our asteroid, 3 times 10 to the 5th meters. And you'll get a pretty big number. I don't remember what these are, but it ends up being at like 10 to the 22nd. Assuming that it has a constant density as a perfect sphere. Now a sphere is 4/3 pi r squared, or pi r cubed. We have r is equal to 3 times 10 to the 5th meters, so we can find the volume. The density is mass over volume. So we had the mass from the last question that we found here, and we divide it by a volume that we calculate there, and you find the density of the asteroid, and you look at what it's made of. I believe it's gold in this problem. Now, finally, a pendulum is initially held at an angle of 10 degrees. So it's held at an angle of 10 degrees. What is the maximum height and maximum velocity of the pendulum if he lets it go? So, as we did before, the maximum height, mgl 1 minus cos theta, is equal to mv squared over 2. And we know what L is, so we can compute this. We know what the angle is, we know what L is, we know what G is. G is not 9.8, it's the G we found here. So we can compute V, and we can compute the maximum height as L times 1 minus cos theta, and V is 2GL 1 minus cos theta, where G is from the previous part and theta is 10 degrees. Now, imagine this last part is totally different. Imagine the same pendulum, but now it's on the surface of a black hole with the same radius. And we want to know what G has to be in order for V to be the speed of light. So if V is equal to 3 times 10 to the 8th is equal to root 2GL 1 minus cos theta, you can find G from this. Square it, you get 3 times 10 to the 8th squared, divided by 2L 1 minus cos theta. That's G. Once you get G, again, you can do G m over r squared will give you the mass of the black hole here. And you end up figuring out that that its mass, the mass at the center of the Milky Way is about 10 to the 36, and I forget what this number gives you. But you can compare the two, the radius of 3 times 10 to the 5th and the mass to the mass of the Milky Way galaxy. The black hole at the center. It's pretty cool. But notice what we did in this problem. We started with something really simple, and that was just finding omega in order to find the period, and then using the period to find the gravitational acceleration on the planet using our simple pendulum. From there, we found the mass of the asteroid, and from that mass of the asteroid, we were able to find the density of the asteroid. Conveniently, it was a sphere. And from there, we could find how fast it should go and how high it should rise. And then from there, we could speculate on what the mass of a black hole of a pendulum moving at the speed of light on the surface of the black hole would be. Event horizon, I should say. So it just flows through. This is about everything you can possibly do with a pendulum that's a simple pendulum. Anyway, another pendulum problem. In this one, we're going to treat G as 9.81. And then we're going to have G on Mars. So a metronome is a thin massless rod. How long must the rod be? So if it's a thin massless rod, we can treat it as a point mass, and I might have messed this up. I don't know if I treated it just as a simple pendulum. I think I did in this solution. You could actually redo this and kind of say, well, it's massless, meaning, it's a mass on the end of a thin massless rod. Sorry, too many problems in the last couple hours. So it's a simple pendulum. This tells you that it's not a physical, it's a simple. Simple pendulum, 2 pi L over G. If we want T to be 1 second, what will L be? So if T is 1 sec and G is 9.8, you can find what L should be. An astronaut lands on Mars and is uncertain what the surface gravity is. He finds that a pendulum with this length oscillates with a period of 1.8. What is the gravity on Mars? So again, if you're given t is 1.85 seconds and length is 0.32, you can find g on Mars as 4 pi squared L over t squared. And then, is the period different than the period on the surface of the Earth? Yes, obviously. Its period is 1.85, and the period here is whatever it happens to be. What is the ratio of the two? And so you know that the period is 2 pi L over G on Earth, and on Mars, it's 2 pi L over G. This is Earth, this is Mars. You can use 9.81. Taking a ratio means dividing them, and this becomes the gravity on Mars over the gravity on Earth and take the square root. The gravity of Mars is like a sixth of the Earth. So this is like 1/6 square root of 1/6, whatever that happens to be. And then finally, this part we've already done a couple times. If you held it at an angle of 10 degrees from the vertical, released it, what's the maximum velocity? Just to remember that you're using g of Mars, not g of Earth there. That's it. Pendulums are easy, like I said. Oscillation is much harder. This is a cool problem. You may not know that the Earth actually flexes. It doesn't actually have a constant radius. Because it's water and it's kind of fluid, it actually bulges, and there's different waves or oscillations that run through. If you take a geophysics class, they talk a lot about these. But one of these waves is like a football. They call them football because they stretch like along the equator. So you have the Earth at some radius, and then it gets squeezed out and it comes back in. And we want to know, we're going to model that as an oscillation, as x of t is x max cos omega t plus phi. So we're going to figure this out. We know the period of this is 3234, and we're going to use that to determine everything else. We know that it is assumed to have a radius of 6.38 kilometers. But first of all, what is the angular frequency omega? Well, t is 2 pi over omega. So omega is 2 pi over t. That's simple. But that's our first of our 3 necessary physical constants to find the equation for the oscillation of the Earth. So 2 pi over 3234 seconds. This becomes a little bit harder. We're going to assume we're in make-believe land, but we measure gravity throughout the day, and we find that gravity has a minimum of which is actually final, but of this, and a maximum of this. So when the Earth is at its smallest radius and when it's at its largest, this is G final, this is G initial. Now G is equal to G mass of the Earth over R squared. And if this is G initial, it's R initial. And if this is G final, this is GM over R final squared. Yeah. Oh, yeah. So we can write this as R final is equal to GM over G final, and R initial is GM over G initial, where M is 5.97 times 10 to the 24th kilograms or whatever for the mass of the Earth. Now, RF minus R naught will give us how much the Earth flexes total. But this is really our D, and we want X max to be D to the half. And you can see that this, if I multiply, this is 1 over GF minus 1 over square root of G initial. You have to be really careful when you do this problem that you don't round, because otherwise that becomes 0 and you get nothing. It ends up being a few centimeters. It really does when you do it. So whatever you get here, divide by half, and that is our X max. So now we have X max, cos, we have omega, and we only need phi. Now here I gave, at time 6:17, I gave what X is, I gave what V is, and I want you to find T. So V over X is again negative omega tan omega T plus phi. You know what omega is. T is given as 1617. You know what V at 1617 is. You know what X is. Plug that stuff in, and you're going to get some tan minus negative V over X times omega minus omega T is phi. That's not too bad. You're going to figure out that it needs to be that tan's going to give you two different, or one angle. You may need to add pi to it. Just make sure that you use a positive angle. If this ends up giving you something negative, add pi to it so that you get something positive. If it's positive, leave it alone. And I forget what that is. But once we find phi from that, we have our equation. We got X max from the change of gravity. We got omega from the period, and we got phi from this equation here. Once we have that, give the equation of the motion, the velocity, and the acceleration. What I want here is I want you to write them out with the appropriate constants here. And I'd prefer that you write them twice, once with just symbols like I'm writing now, and then once with numbers, like equals, and put what X max is, put what omega is in there. So you have a numeric equation that you can use. This is probably one of the harder questions to understand. What time after t is equal to 0 is gravity is a minimum? When gravity is a minimum, we already said that x is at a maximum. So if x is going to be at a maximum, then, and I should say that when it goes out, gravity will be at a minimum. When x is at a maximum. What time is the radius of the Earth, or what time? So I want to know when x is max occurs, and I want to know when v max occurs. Those occur, so since x is equal to x max cos omega t plus phi, as it says here, well, I didn't write it here, but x max cos. This is a maximum when cosine is a maximum, and cosine is a maximum when omega t plus phi is equal to either 0 or pi. Go ahead and use 0 here. And what we get is that omega t is equal to negative phi, or t is equal to negative phi over omega. And then when the velocity is the max, sine of omega t plus phi has to be pi half, because sine of pi half is 1. So if omega t plus phi is equal to pi half, then t is equal to pi half minus phi divided by omega. And you can find the time right away. It's not too hard to find the time, as long as you know your phi. So our last one here are tuning forks. And we're told, again, the frequency is 440. If you don't know what a tuning fork is, back before they had really good electric tuners, you would have little things you could blow to get the right tune or the right note to tune your guitar or violin or whatever have you to. And one of the cool things they had was forks. So they looked like a fork with 2 times you hit them and you would hear the A note or whatever note the fork was tuned to. And then you could tune your guitar to it. So the frequency is 440 and we're told that X max is 0.044. So we're given that. We want, assuming at t is equal to 0, x of t is equal to 0. Now, in order for this to happen, notice something. X of t is equal to x max cos omega t plus phi. And if this is 0, in order for x max to be 0, phi can't be 0. If phi were 0, we would get x max. So what does the phase angle have to be? It either has to be pi half or 3 pi half or, I'm sorry. Yeah, in order for this to be 0 or -3 or negative pi half, you know, it could be some multiple of this. It says to choose the smaller value, just choose this pi half. So we're going to say that phi is pi half. And we know that because we're assuming that when t is equal to 0, x is equal to 0. We're just starting to measure our time when the prong is at 0. What is the position x of the prong after 3 seconds? Well, x of t, we already have x max. That was given to us. Cos, we have phi, is pi half. So what is omega? Well, f times 2 pi is omega, so omega is 2 pi f. Plug that in, and you get omega t plus that. Plug in for t3, and you're good. It's not too hard. Maximum velocity and acceleration we've done a couple times today. This is omega x max. This is omega squared x max. What is the value of k of the prong if m is 0.001? So omega is root k over m, or omega squared is k over m, or k is m omega squared. And what is the total energy? That is k x max squared over 2. We have k, we have x max squared. And then this final term is jerk. Now we said that a of t was negative omega squared x max sine omega t plus phi. If we take another derivative with respect to time of this, what do we get? This sine becomes cosine. I'm sorry, I'm being dumb. It's cosine. I'm like, why doesn't my plus go away? If we take a derivative of cosine, we get a negative sine. We get another omega, so we get omega to the third. Sine of omega t plus phi. We know the position is x of t, and we know the time derivative of the position of v of t is the velocity, or how fast it moves. The next time derivative is of the velocity is the acceleration. So dv dt, we learned that day 1 or for a couple weeks. So the change of the speed is the acceleration, but what is the change of the acceleration? Well, they call it jerk. And basically it's how fast the acceleration changes, which you guys have already seen in the lab. Sometimes our system had like a little bit of lag as the acceleration was actually changing. If you didn't notice that, it was lagging the system or whatever. But it's basically how fast the acceleration can change. It's almost never used. The only time it's used is in engineering, really. Engineering has a couple times where they use jerk. What is the maximum value? omega cubed times x max. Why is it important? And it's important for engineers to know because it can actually measure the amount of stress something's under by how much a force is going to hit it. This question, it's important to know how fast a force can change things. I didn't expect a lot of students to understand like why it might be important, but if they gave me an answer that seemed reasonably well thought out, I gave them credit for it. So if you get any questions like that and you don't know how to answer them, give it a shot. There's usually not a wrong answer as long as you give a thoughtful, short one-sentence reply. Okay. From that, I'm done with the problems on the final and the homework, but I did want to go back. Uh-oh, don't do that, James. Sorry if someone saw someone's grade that they shouldn't have. I did want to go back and just talk about a couple of things. In the modules for the practice exams, and I'm going to let you guys do this. Practice exams. So this practice final 2, it says here. If you look at the structure on here, question 1 was a Newton's laws. All you had to write was the free body diagram for A, B, and C. A obviously has a tension and a force of friction and a normal force and a weight. B has a tension going that way and a friction force going to the right, a normal force up and a weight down. And then C has a weight down and tension up and down. You guys should know how to do those free body diagrams, how to write Newton's equations from them. But just go back through if you don't remember how to do it, and try these again. This scenario 2, we're adding a spring and we're trying to figure out when A is 0, how far the spring would be stretched. In this case, you would treat the friction as static friction, even though it's kinetic and static. I didn't differentiate between the two in those. This one you don't have to worry about. It's an equilibrium problem. We will not have equilibrium on the test. These ones for the other practice final are much, much harder than what was just there. And it's good that they're harder. So basically, you're going to write the torque diagram and the free body diagram. Just review how to write those for these. And the nice thing is, this system is exactly the same as this system. And that's what I wanted the students to get out of these two when they took this test for their final. That we have this system of 3 different pulleys with 3 different masses, but they're attached and they all have the same alpha. So just go back through that and go through these problems. I don't think these are too hard. As I said in my announcement, there is a, I forgot a couple weeks back, there is a solution to exam 2 on here. I don't know how much exam 2 is going to help because if it will ever load. Did I stop sharing? Yeah. Yeah, so sorry. Can you see my screen, Eric?
Yeah, we can see your screen.
Okay, cool. So I put up the exam 2, and again, exam 2 solutions. This first one's equilibrium. We probably won't have equilibrium. there's a nice short energy rotation problem that's probably good to review. But remember that when I wrote it and I realized the morning of the test when I gave it to you guys that H1 and H2 had to be equal because of the way it was connected. And so this part's X'd out, but I believe I answered it correctly with H1 equal to H2 if you wanted to know. Although I gave everyone credit on that one because I was being dumb. These collisions aren't helpful because I'm not going to put collisions on there. Angular momentum's worth reviewing. That problem's a bit of a bear. That was a really hard problem. This problem's really, really, I urge you all, especially those who watch the video who are still here, this energy problem at the end, make sure you know how to do it. Make sure that you remember how to do projectile motion, because projectile motion is going to be on there. And in fact, I hope you all remember, because we do have to do that quiz that we took day one over again. And hopefully more of you will get it right than got it right day one. Hopefully you learned how to do projectile motion. But yeah, so study really problem 5 is useful. Problem 4 is a little useful, but no collisions. Problem 2 is useful if you don't remember, if it's been a while since you thought about how to do a problem with pulleys that turn. And the one thing that's not on here is you might want to review inclined plane with a pulley, like a pulley in an inclined plane. But otherwise, really just make sure you know the homeworks that we've gone over, 13, 14, and 15. At the very least, you know which problems cover which concepts. Because the test will be the same as test 1 was, where we're going to be in class. You're going to be in class with your camera on, so that I know you're all working on your own. And you'll still be able to use your book, and you'll be able to do, like, look up the solutions to the homeworks or the solutions to the practice exams if you need them, or your book. So just at the very least, if you're having a lot of other finals and stuff, make sure you know where to find the answers you need for those types of problems, and make sure you've done the homework. I'm going to right now, before I forget, I'm going to move homework 15 back to the night of our final, just to make sure people have time to do it. And as I said, if you have a question about your grade, like the homework that you haven't turned in, if you want me to open something up, let me know. But as I said in the announcement, if you think if you're missing 5 or 6 homeworks and you think you're going to do them this weekend, you're probably not going to, although I'll open them for you. I would rather you do them and use them to study. But anyway, good luck. For those of you who are still here, and I know it's only a few of us left, particularly Alexis and Eric, Emilio, Brandon, and Ariba, thank you guys for that wonderful, touching thank you at the beginning of class. That was
Thank you so much for all you've done.